So hello, everyone. It's my pleasure to introduce the next speaker, Professor Jacek Gondzio from the University of Edinburgh. He's going to talk about the recent advances in iterative solvers for interior point methods. So please go ahead, stage is yours.
Thank you. Thank you very much. I hope you can all see my slides fine. I have prepared about 60 slides for this talk. I know the talk is supposed to last up to 2 hours, but I think there is plenty of time for any of you having questions in the middle of this talk. So if there is any issue that you find problematic, or if you spot an error in my slides, just don't hesitate to interrupt me and ask your questions or point to an unclear thing. Right. My talk will focus on recent advances in iterative solvers employed inside interior point methods. So as you can see from the title, it will be pretty much a computationally oriented talk. In a way, it may be a bit different from many of the heavily loaded mathematical, theoretical talks that you have seen earlier during this week. Here's the outline of my presentation. At the beginning, at the start of it, I would like to convey the key ideas of interior point methods to you, and I believe most of you have followed some kind of undergraduate or postgraduate course on interior point methods, and you certainly have seen how beautiful these methods are. But I somehow insist on reviewing a few of the main building blocks of it, and I would like to give you a computational perspective, because this would then allow me to move on to the big item 2, which will concentrate on the use of Krylov subspace methods and design of preconditioners for such methods. Finally, in the last third part of the talk, I will go beyond the obvious things and will address those 4 items, which are how much of interior point do we really need in interior point? Can we be a little bit more flexible? Can we be permissive regarding dropping some of the assumptions normally used? And I will then talk about very, very inexact interior point methods and also primal dual Newton conjugate gradient. To finish up with a variety of applications which originate from sparse approximations, all of them solved with interior point methods. Right, so let me start from this. It will soon be 40 years since this fantastic paper was produced by an Indian origin researcher at AT&T Bell Labs. But what we know today is that in a way it was a shocking mathematical concept, because he considered a linear optimization problem, but he proposed to use a nonlinear function, to add a nonlinear function to the objective. And when you think of it, it is such a counterintuitive step. And maybe that's why it was so difficult to design interior point methods. But what I'd like to say is that this is definitely a step against the common sense, against the centuries of mathematics, because what Karl Markov proposed is something like non-linearizing the linear problem. And that's very much against what we normally do in mathematics. We frequently have a nonlinear problem and we simplify it by linearizing it locally around a given point. But doing the opposite, that's certainly a very clever thing to do. If you do it, then you will achieve something, but to appreciate what will be achieved, First of all, I need to refresh your memory on this very basic connection of duality and its manifestation in the context of linear programming. So consider two linear programs, primal and dual. These are the twin siblings, twin brothers or twin sisters, if you like. They are connected through the Lagrangian. Here is the Lagrangian function associated with those two problems. And the closely related optimality conditions for both these problems, which require primal feasibility. Oops, I cannot underline like this. Primal feasibility, AX is equal to B. Dual feasibility here. And the third condition, which is a complementarity condition, which requires that for every component J, either Xj or Sj should be zero. The product Xj, Sj should be zero. It is written here in the notation which is common for interior point literature, in which a capital X is a matrix where on diagonal of this matrix, the elements of the vector are placed. I will use this notation quite a lot in the subsequent presentation part of the presentation, so please get used to it. Remember, capital X is the diagonal matrix here with elements of the vector X. Similarly, capital S is the vector where S's are on the diagonal. And the vector E, which you can see here, is the vector of ones, all of course in consistent dimensions. So one short way of writing this requirement that Xj, Sj has to be equal to 0 for every component J is to write it in this vector notation. Matrix, actually, matrix vector notation. Capital X, capital S times E is equal to 0. Now, I mentioned all this because we will now perform a very simple exercise that is use the logarithmic barrier function, this clever nonlinear function, to slightly alter these optimality conditions. Now, how does it go? The great thing about logarithmic function is that it can provide us with a barrier. If we use a minus logarithm function and we try to minimize it, then necessarily we will be moving away from the boundary, moving away from xj getting close to 0. So we may say that the logarithmic barrier replaces this inequality. It does not allow the variable xj to approach 0. It creates a barrier on it. And here is a quick, really very elementary observation. If I have a vector x and I would like the whole vector to have non-negative components, all non-negative components, then I could penalize the sum of all the logarithms, and the minimization of this minus sum of logarithms is equivalent to the minimization of e to the e is the Euler number, e to such a power. And then you do the usual thing, that is e to the logarithm of x is just x. And this turns out to be equivalent to maximizing the product of xj's. So what this sum of logarithms would contribute in a linear programming context is that it would keep all variables xj, which have to be non-negative, it would keep them all far away from 0, because if any of them approaches 0, the whole product will quickly go to 0 as well. So the minimization of the sum, written like this, is equivalent to the maximization of the product of distances from all hyperplanes defining the positive orthant. And in effect, it prevents all xj's from approaching 0. So that's a concept, that's a very obvious explanation of what logarithms can deliver to us. And now, if we do have these logarithmic functions, then we can replace the primal LP, which is written here, which has non-negativity constraint, with a different problem. With a problem in which non-negativity constraint is dropped, removed, and replaced by the presence of this new term in the objective function. The new term which is me times the sum of logarithms of xj. The barrier parameter, this Greek letter me here, will control how strong we would like this logarithmic barrier to be in relation to the true objective of the problem. Observe that as long as me is a large number, I would mostly focus on keeping xj as large as possible and the point as central as possible. However, if the barrier parameter me starts to decrease and goes smaller and smaller, gets closer to zero, then of course the whole force of logarithmic barrier will become negligible and we will see more of the linear object. Right, that's the concept behind interior point methods. And to derive the first order optimality conditions for this problem, we will have to write the Lagrangian, which of course takes the usual form with the objective and Lagrange multiplier multiplied with the equality constraint. And on my next slide, I will ask for conditions for a stationary point of this Lagrangian. That is, I'd like to guarantee that I find a saddle point of the Lagrangian, and this will be guaranteed if the derivatives of the Lagrangian with respect to x and y are 0. The derivative with respect to x is the most interesting object that I'd like to draw your attention to. Differentiate this function with x and you will obtain c, from here a transpose y, and from here, of course, the terms 1 over x multiplied with the scalar me. Indeed, that's what you can see here. This is the me times x inverse e as the last contribution from this differentiation, where I use the typical notation. Capital X inverse means that this is the matrix where on the diagonal of which we have inverses of entries of the vector x1, x2 up to xn. Please remember that we keep all the x's strictly positive. Of course, we have to keep them that way because otherwise the logarithm would not be correctly defined. And after a substitution in which this object, me x inverse e, is replaced with a new letter s, which, by the way, is equivalent to saying that capital X times capital S times E is equal to me, we obtain the first order optimality conditions for the barrier subproblem. And here I would like to draw your attention to the fact that now we are not asking here for XSE to be equal to 0, but we have here contributed a perturbation. What we now ask for is that all the products xj times sj should be the same and equal to the same value of this barrier parameter me. You've noticed that I pronounce this letter me, not like many people do, not mu, but this is in fact a Greek letter. So just to argue for the correct pronunciation of it, let me refer you to Robert De Niro and his film Taxi Driver. By the way, a very violent film, but won several Oscars for Robert De Niro, for Jodie Foster. So if you have never seen it, you might like to see it. Robert De Niro was saying something like, "You're talking to me." So please remember, that's the best pronunciation of Greek letter me. But going back to my interior point methods, we will now have a new form of first order conditions in which complementarity, previously with a 0 on the right hand side, is now different. Complementarity condition is now really not a complementarity condition. It is the condition saying that the product of xj times sj for every component j should be equal to the value of the barrier parameter. And this is the essential difference compared with the simplex method, or more broadly, with any kind of active set method. In active set method, you have to make a guess which of those two, either x or s for every component, is equal to 0. In interior point method, we never guess. We will just use the barrier here, and the barrier will be pressed, will be squeezed to make it smaller and smaller. Eventually, I mean, at convergence, me will get so close to 0 that we will be able to say that this condition tends to satisfying such a condition with a 0. This is the huge difference when you compare interior point and active set methods. And by the way, this is this miraculous trick which allows us to avoid the combinatorial difficulty related to active set method. Combinatorial difficulty here translates into the need of choosing which variables are basic, which are non-basic. In other words, how are we going to satisfy x times s being equal to 0 for every component? In interior point method, we do not have to perform this choice. We do not have to perform to make such a commitment. Instead, we will keep all the products close to the same value me, and we will gradually reduce this value until it gets sufficiently close to 0. There is an important notion called central trajectory, which is associated with this value of the parameter me. First of all, let me draw your attention to the fact that if we have primal and dual feasibility, then the duality gap will just be equal to the complementarity gap. And because every product xj sj is equal to me, and we have n such products, then the scalar product, the full complementarity product, will just be equal to n times me. So from here, you also immediately notice that the way to reduce the barrier term me would also mean closing the duality gap in linear programming. This would mean that if me goes to 0, then the minimum of the primal gets close to the maximum of the dual. So we find the optimal solution. I want to underline under the assumption of feasibility of x in the primal and the feasibility of y and s in the dual. With every parameter me, this system of nonlinear equations has a unique solution, and we could write this solution parameterized with the value me. So if we do it, if we write it that way, x depending on me, y depending on me, and s depending on me, it would define a unique point. And moreover, if we then allow the parameter me to grow, to go from infinity to 0, this will define a continuous curve, which is called the primal dual central trajectory. It has an importance, this central trajectory, because implementations, algorithms based on interior point methods do follow this path. This trajectory gives us a very useful guidance how we can approach the optimal solution. And the best algorithms try to follow the central trajectory and try to never get too far away from the central trajectory. What does it mean not to go away from central trajectory? It would mean that we will try to satisfy to perfection primal feasibility and dual feasibility, but this last condition here would mean that we would like to keep all the complementarity products approximately the same and equal to the value of barrier parameter me. We could define the neighborhood, which the set of points which are close to central trajectory. If we just replace this approximate satisfaction of an equation with an admissible error in this equation. So here we say that the norm of the error in this last equation should be small. To be more precise, should be smaller than some fraction of the barrier parameter mi. Such a definition of central trajectory is a little bit unusual, and it's worth drawing our attention to the fact that the size of this neighborhood reduces as we move closer and closer to the optimal solution. That is, when mi goes to 0, we also ask for being closer and closer to the central path, because the radius of this ball around the central path decreases as mi decreases to 0. An enjoyable feature of interior point method for linear programming is, of course, its polynomial guaranteed polynomial worst case complexity. This one is achieved because if the algorithm stays close to the central path, that is, if we limit the moves of the algorithm to the N2 neighborhood of the central path as defined on the previous slide, and if we are very conservative and ask for a small reduction of the barrier term from iteration k to iteration k plus 1, which here is expressed by saying reduce mi k merely sigma times, where sigma is some number very close to 1, then we will be able to prove that interior point method converges to optimal solution very quickly, converges in O of square root of n iterations. And again, I'm not going to give you a detailed proof. You can find it in fantastic books on interior point methods, but the argument, mathematical argument, is just that simple. If we ask for such a reduction at a single iteration, by the term sigma, which was defined as 1 minus beta divided by square root of n, that after square root of n iterations, we will power the sigma to the square of n, and this will already give us a noticeable reduction, a number which is noticeably smaller than 1. Then a constant times square root of n iterations would give us an arbitrarily good reduction of the duality gap. Well, in the say, less rigorous mathematical parlance, we may say that this iteration complexity O of square root of n means that after the number of iterations proportional to the square root of n, the algorithm will solve the problem. To be more precise, will solve the problem to an arbitrary precision, arbitrary accuracy we ask it to achieve. Well, I focused so far on linear programming, but the beauty of interior point methods is that they can be very easily generalized from LP to quadratic programming, then to convex non-linear programming, and also a variety of conic problems, like second-order cone problems or semi-definite programming problems. The trick is in finding the right barrier function for the right inequality. So, for example, in second-order cone programming, when we write the quadratic cone and we have this inequality that needs to be satisfied, then to force this inequality to be satisfied, we will use the logarithmic penalty on the non-negative term, which you can see in this inequality. So we will ask for we will ask for the use of the following logarithmic barrier function, which is the logarithm of t squared minus the norm of x squared. If we think of semi-definite programming problems and positive semi-definite matrices, then there also exists a beautiful logarithmic barrier function for these problems. And in this case, we will ask for the logarithm of the determinant of the matrix X. Because if we want to keep X positive, strictly positive definite, then the determinant of X should be kept as large as possible, which means minus logarithm of it should be as small as possible. Well, here the connection is very elegantly explained by thinking what happens in LP. In LP, we had this simple inequality, x greater than or equals 0, and we replaced it with the logarithm of xj for every j. In semi-definite programming, we ask for the matrix to be positive semi-definite, which is equivalent to saying all eigenvalues of this matrix should be non-negative. And now all eigenvalues non-negative would be just an inequality, lambda greater than or equals 0. So we take the sum of logarithms of all the lambdas. But the sum of logarithms of lambdas is the logarithm of the product of lambdas. So the product of all eigenvalues of the positive definite matrix gives us a determinant of this matrix, which explains this form here. So that's a beautiful thing about interior point methods, that we can generalize them from linear programming to quadratic, non-linear, second-order cone, or semi-definite programming. In my next few slides, I'd like to show you what happens in terms of computations in interior point methods. So I will once again move back to linear programming and recall the form of first-order optimality conditions for the barrier problem. You remember we asked for primal feasibility to be satisfied, dual feasibility to be satisfied, and complementarity. Oops, I cannot underline complementarity. Complementarity condition, perturbed complementarity condition to be satisfied. This is just a system of non-linear equations. The first two are linear. The last one is not. The last one is the bilinear constraint. And for this system, for this large function operating in a large space, we will write the Newton method. So the Newton method will require differentiating this object, writing the Jacobian. Jacobian times Newton direction is equal to minus value of the function. That's the definition of Newton direction. And this is the computational kernel of interior point methods. In practice, we will reduce this system by eliminating delta S, and after this step is performed, we will obtain this augmented system version, which is a very typical linear equation solved in many areas of mathematics. When you think of it, why does it resurface in so many areas of mathematics? Because I think so many areas of engineering and computational mathematics actually look for some sort of minimum, some sort of optimum. And of course, the optimality conditions will always give the same thing. Well, there is a great similarity between linear programming and quadratic programming and non-linear programming, because we always have to solve a system of that type. Optimizers call it the reduced KKT system. But if you talk to your friends and colleagues who do PhD in partial differential equations, they would call it a saddle point system. There's a vast literature about it. I think actually probably way more papers which address the saddle point system in PDE context. But from computational perspective, we are talking here about some sort of weighted least squares, which is the basic computational tool in so many areas of mathematics. Well, let me wrap up this intro to interior point methods. What they deliver is a unified view of optimization, which goes through different classes of optimization problems. They have predictable behavior. Amazingly, they always solve the problem in a very small number of iterations. They have unequal efficiency. They are certainly competitive for small problems, anything below 1 million. But if you want to go for really large scale problems, accessing 1 million in dimension, then practically nothing can compare with interior point methods. And already many years ago, almost 2 decades ago, a size of 1 billion was reached. If you are interested, you can have a look at the paper and the related software which was used to do that. In the rest of my talk, I will talk about improvements of interior point methods and the improvements that happened over the last, say, 5-10 years. And those concentrated on using the second order information, that is using the Newton direction, but relaxing the rigor of doing this. That is not always going for the exact solution of Newton's system, but admitting that we may solve the Newton system inexactly. We can accept certain control error in it and still benefit from many advantages of the Newton method. This is based on something that is very well known and very widely accepted, an inexact Newton method in a broad context of optimization and solving nonlinear equations. It's an old work of Denbo, Eisenstadt, and Steinhaug, but it has also been relatively early spotted by Stefania Bellavia that it can be used in the context of interior point methods. The inexact Newton method here in the context of interior point methods. Main tool that I'm going to use will be indeed the inexact Newton method, which means that rather than solving Newton equation exactly, we will allow that there is certain error in the solution, but we will ask for this error, R, to be bounded by the right-hand side, to be only a fraction of the right-hand side, a fraction eta of the right-hand side vector. As long as we do not solve the Newton for Newton direction to perfect accuracy, but we solve it for this accuracy which is subjected to an error which is merely a fraction of the right-hand side, practical inexact Newton method behaves almost as well as the exact Newton method. There are some mathematical consequences. Instead of having quadratic convergence close to the solution, we will have to accept only superlinear convergence, but this is not a big deal. It's not something that should put us off from using the inexact Newton method. Well, whenever you try to do such a thing, that is replace Newton method with an inexact Newton method, you should, of course, ask yourself the theoretical question: will it impact, for example, worst case complexity of interior point methods? Will it affect adversely the practical performance? And the answer is no. It does not affect the complexity result, and it is also helping, as a matter of fact, practical performance. And here's the theorem which tells you what will happen if we replace exact Newton direction with an inexact Newton direction. So as long as we use the so-called short step method and we operate in the small n2 neighborhood of the central path, we could accept the error in Newton direction, which is surprisingly up to 30%. So very admissive, very permissive error here, and we do not lose anything in terms of complexity of the interior point method. It still remains being O of square root of n. If we use a symmetric neighborhood, this is a much more attractive neighborhood of the central path used in all practical implementations of interior point method. Here is a definition of it. We ask here every complementarity pair to be not too small compared with me and not too large compared with me. So every xi, si can be a little bit smaller than me or a little bit larger than me. You see the symmetry, gamma times smaller or 1 over gamma times larger, then we can, for such a neighborhood, we can accept up to 5% error in the direction, in the inexact Newton direction, and this does not affect the complexity result. The details of it are in the paper if you are interested in. Now, before I move to the next part of the talk, I will go back once again to computational view of interior point methods, but maybe this is a good point to make a little break of 2-3 minutes, 5 minutes if necessary, and ask you whether you have any questions concerning the first, roughly speaking, 1/3 of my talk. So is there anybody who would like to ask a question? No?
Hello.
Yeah.
I already heard about quasi-Newton methods. Is it
Yeah.
the same?
Quasi-Newton methods are...
I don't know if it is a normal name.
It's a special type of inexact Newton method. It's a situation in which instead of the true Hessian of the problem, you use a low rank approximation, typically a diagonal matrix plus low rank approximation of the earlier computed Hessian plus low rank approximation. So quasi-Newton methods are very attractive broad class of inexact Newton methods. I actually studied them, and well, I do not mention it here, but there is a paper we wrote together with a colleague from Brazil, Francisco Sobral. If you check my website, you might find it on quasi-Newton interior point methods.
Thank you. Yes, I already heard about him. Thank you.
Maybe I also have a quick question, Jacek.
Yes, Mikhail, can you speak up, please?
Can you hear me?
Yes, now I can.
Okay. So talking about these constants you mentioned on the previous slide, these 5% of an error, is it somehow sharp? It comes a little bit as a surprise that it's precisely 5% error allowed.
Yeah, well, listen, it was a big surprise to me as well, but I think what you should keep in mind is that we are only accepting the error in the centrality condition, because we are talking here about strictly feasible solution. So both these analyses were done for feasible algorithm and for linear and quadratic programming. If you deal with nonlinear optimization or anything originating from PDEs, as you would probably be interested in, then maybe more conservative eta would have to be used.
Yeah, I understand, but why? Can you give me an idea why precisely 0.05? So, or is it just that 0.04 would be sufficient as well? So, can we see somehow?
Well, the numbers, I chose these numbers in the analysis to no, they do not have any special meaning. So 30% was just a convenient thing for me to derive all the necessary inequalities. If you push it, you might be able to say that that there is 37% allowed here, or I don't know, 7 or 8 or 9% allowed here. I just didn't pay that much attention to it. So the numbers are a little bit arbitrary.
Okay, thanks a lot.
Etienne?
Jacek, I have a question. First of all, it's nice to see you again. So I just have a wondering that these results for the inexact Newton method. So you cite a paper here dealing with convex quadratic programming. So are you aware of more general results?
More general results for using inexact Newton methods?
Yes, and interior point methods for more general problems.
I'm not aware if people tried it for conic problems. It would really surprise me if it did not, if for whatever reasons it did not work as well as it does for.
No, because I just want to mention that together with Francois Glenure and Adrian Taylor, we did a work just quite recently where we just analyzed the approximate inexact Newton method for self-concordant functions.
Mm-hmm.
And then we could show that, essentially also you do not lose much. So maybe that's also of interest to you. I can send you the reference if you're interested.
Thanks a lot.
Thank you.
Again, me too, please.
It does not surprise me because adding any kind of prox terms would not affect self-concordance. I mean, the typical quadratic prox should not affect self-concordance, so it should not affect the complexity result. But on the other hand, adding prox would make the use of inexact Newton easier. Yeah. Any more questions, or should I return to slides? Well, let me continue. So we were here, and I wanted to once again focus on computational perspective on interior point methods, but this time the focus will be really on iterative solvers and the design of preconditioners for these solvers. And let me just mention that there is a nice survey paper of Italians, Marco D'Apuzzo, Valentina De Simone, and Daniela Di Serafino, who looked at all the linear algebra aspects of large-scale interior point methods. So you may have a look at it. Right, let me go back to linear algebra of interior point methods in a simple case of LP or QP. So we have to solve the Newton equation, which is written here, and this Newton equation will be, after eliminating the last component, delta S, oops, I cannot indicate it, the last component, delta S, in the unknown vector, you eliminate this and you will obtain this augmented system in such a form. Or if you continue the elimination and you try to remove delta X from this equation, you will obtain so-called normal equations, or the sure complement form of equations. But in both these cases, there is a slightly frightening matrix theta appearing here, where theta is defined as X divided by S for every component. And let me remind you, X is the primal variable, S is the dual slug, or the Lagrange multiplier associated with inequality X greater than or equal 0. So this matrix theta always behaves rather badly. It has bad terms. I will explain it in a second. But what we'd like to do is to use Krylov subspace methods and solve either the augmented system or normal equations. If we want to go for augmented system, we have to accept that the matrix here is indefinite, and this impacts on which Krylov methods can be used. So it can be the minimum residual, or the generalized minimum residual, or the quasi-minimum residual method. There is a family of these methods known well in linear algebra community. However, if we deal with normal equations, the situation is slightly more favorable, because normal equations, by definition, for convex programming at least, are guaranteed to give us a positive definite matrix, so we can use conjugate gradient. And that's definitely a very well-known method, which has nice features. Quick convergence. Quick convergence under the condition we know how to precondition it. But I already flagged the difficulty. The difficulty originates from this matrix theta, which is equal to x divided by s. Now, recall that the product xj, sj, all the products for all components j should be approximately equal to the barrier parameter mi. So if we then consider so-called basic variables, basic not understood in the sense of the simplex method, but those variables which converge to a strictly positive solution, then necessarily the corresponding Lagrange multiplier will have to go to 0. And what will happen to this theta? Theta, defined as xj divided by sj, can be written as xj squared divided by xj sj. Xj squared will give us a number O of 1, of order 1, but divided by mi. So this will behave as O of mi inverse, where mi, remember, converges to 0. So this is the bad news, because it means that theta will go to infinity. On the other hand, for non-basic variables, we know that those are the variables which converge to 0 at optimality, but then the dual slugs will be strictly positive. And in such case, we will have theta, which is xj divided by sj, and now we can write it in the form xj sj divided by something which is O of 1. So this will behave as proportional to mi, proportional to the barrier term. And this means it will go to 0 when mi goes to 0. So unfortunately, to summarize, this matrix theta, which appears in interior point methods, behaves very badly from numerical point of view. Some elements of this matrix go to infinity, others go to 0. This means that the condition number of this matrix inevitably will go to infinity. The condition number of this matrix inevitably will go to infinity. This is not good news when you want to solve these systems. This is even worse news if you want to solve these systems with iterative methods. But sometimes, if you have a trouble, sometimes it's possible to convert a difficulty into an advantage. Because these thetas behaving so badly, some of them going to infinity, others going to 0, actually tell us something. They hint what the optimal partition in the problem should be. And a spectacular feature of interior point methods is that this optimal partition is relatively early revealed by any practical algorithm. And therefore, if we can reveal the optimal partition, we might be able then to gamble and to say, okay, this tells me which part of the solution is basic, and this tells me which part of the solution is non-basic. This was very nicely done by the Brazilian researcher working at Rice University in his PhD thesis, and there's also a paper by Aurelio Oliveira and Dani Sorensen. And that's how it goes. You look at normal equations used in linear programming. Normal equations in LP would have this form. But what does it mean that we perform the multiplication A theta A transpose? We can unfold this multiplication and write it as the outer products. That is theta j times rank 1 products for every column j. This product, Aj times Aj transpose, is a rank 1 matrix corresponding to column j of matrix A. And this is pre-multiplied with theta j. But if we know that basic part of theta j goes to infinity, non-basic part of theta j goes to 0, then we may say the whole second object here, the second part and this summation is actually negligible compared to the first one. I'll say it once again. Theta j for basic part goes to infinity. Theta j for non-basic part goes to 0. So we may all these terms that are added here are negligibly small compared with those ones. Well, this means that we could approximate maybe the matrix like this by taking only basic part of thetas. So only a subset of variables will really determine the behavior of this matrix. And this has indeed been used by Oliveira and Sorensen to design a preconditioner for augmented system. And now I do realize that there is a lot of linear algebra on this slide. So what you have here in the middle is the augmented system corresponding to the linear programming problem, in which the matrix A has been partitioned into basic and non-basic part. Please do not interpret basic, non-basic as in the simplex method. It's a very different partitioning. I only use this basic, non-basic in quotation. And this matrix can be pre-multiplied and post-multiplied to preserve symmetry by the appropriately chosen preconditioner from the left and preconditioner from the right. And if we do it, then a little bit of linear algebra, nothing frightening, but requiring a little bit of patience, would convert the matrix to this form, in which everything on the diagonal comes down to identities of appropriate dimensions, but there is this off-diagonal block W. And W is defined like this, but may I just remind you, we know that when the barrier term goes to 0, then theta b goes to infinity, so theta b inverse goes to 0. Theta n goes to 0. So you see, in W, we have here a small term multiplied with some matrix and multiplied with a small term again, which means there's serious hope that this matrix W will be approximately equal to 0. And indeed, we do observe it, that the closer to optimality the algorithm gets, the closer this W gets to 0. Such a preconditioner can be implemented. It was implemented by Oliveira and Sorensen, and it actually works quite okay. But there is a difficulty, which is how to guess this basic and non-basic partition. And it's not just that we have to guess the partitioning, but we have to make sure that the basis matrix is invertible. And I would say even something more important, it is invertible without contributing too much of numerical errors. So writing everything down in mathematics would give us that using this as a preconditioner for the normal equations gives us such a preconditioned matrix, and this matrix would be close to identity. So that's very good for Krylov methods, as long as the matrix W is small. But how to choose the matrix B, how to choose theta B, that's a slightly problematic thing. So what was originally done by Oliveira and many other authors is that they proposed to look at thetas and just order thetas from the largest to the smallest and pick the largest ones to contribute to the basis matrix. It sounds easy, but the trouble is that if you select the basis that way, the basis is not a non-singular matrix. The basis is singular, which just reflects the fact that linear programs are often very highly degenerate. This is the choice which I would call the maximum weight, because we are looking at the weight of matrix theta and choose the maximum weight. We follow this argument, this rationale. It's been done by many authors, including my own PhD student, Gusson Al-Jairud. But it's much better to use some more sophisticated feature of the matrix and choose the so-called maximum volume, where maximum volume means that we would like to choose beta times square root of theta b to have as large volume as possible, where volume is understood as a determinant, volume of the matrix is understood as a determinant of U transpose. If we do this choice, then we can obtain a significantly more stable basis. However, the trouble is that maximum volume basis, choosing the maximum volume basis, is an NP-hard problem. So what I have proposed so far is to replace an easy LP with a hard NP-hard problem of choosing the maximum volume basis, and you have to reject it immediately. It's not doing any good. But what we could do is relax this maximum volume requirement, replace it with something that is computable, which is called a local row maximum volume basis. Local row maximum volume basis is the basis AB such that when you compute AB inverse times the matrix A, the largest element in this matrix cannot exceed a given parameter rho. So it will not be the maximum volume. For maximum volume, rho should be 1. If you ask for 1 here, it's a hell of the job. It would require NP-hard. It would be NP-hard. But if you require rho to be equal to 1.5 or 2 or maybe 10, then this can be reasonably quickly computed. And the advantages are that it can be done using simplex type updates. So working with unsymmetric factorization of the matrix B, or the candidate matrix AB. And it has been implemented by my PhD student, Lucas Schork. It actually works very well. Here in this paper, there is a comparison against Gurobi. Actually, this implementation of interior point method with inexact Newton direction computed by this row maximum volume basis delivers the method that sometimes can even beat Gurobi. It's very difficult, believe me, it's very difficult to compete with commercial codes. So I cannot say that we beat it regularly, but there is a noticeable percentage of problems on which this methodology is faster than Gurobi. There is also a noticeable percentage of problems on which it is not. So yeah, Gurobi is still a very good interior point solver. But now I'd like to move to a more general perspective and talk about the general preconditioners. What do we normally ask from a general preconditioner is that we will have to solve a linear system like this, which involves certain matrix M, unknown U on the right-hand side. So here is the equation system we'd like to solve. And we would like to find a preconditioner, a matrix P, which reasonably well approximates the matrix M. The typical requirement for the preconditioner is to say, oh, we would like to achieve this. We would like the inverse of P to be such that inverse of P times M would give us something close to identity, if not very close to identity, then maybe differing from identity by a rank 1 matrix, low rank matrix U, or maybe some other form of perturbation, the matrix F, which has small Frobenius norm. If you manage to construct a preconditioner which satisfies these conditions, then Krylov subspace method is very likely to give you a quick solution of the system by the appropriate preconditioned method. By quick solution, I mean the solution after not too many Krylov subspace iterations. And the design of preconditioners is often based on realizing that there are some particularities of the matrix M. Here, unfortunately, we step into high level of specialization of specialized techniques. That is, if you know something about the matrix M, you might be able to translate this knowledge into designing a clever preconditioner for it. I didn't mention it here on the slide, but we would like the preconditioner to be significantly simpler than M. it doesn't make sense to replace m with here with the preconditioner equal to m, because it would mean we solve the system directly. But we want P inverse to be quickly computable and such that P inverse m has this favorable structure. So in the rest of my talk, I will not be in detail presenting the preconditioners, but I will show you a number of applications in which this approach could have been implemented, was implemented, and it led to sometimes spectacular computational results. Before I go to this, I'd like to somehow wrap up the interior point part of the talk, this basic interior point part of the talk, with saying that what is an amazing feature of interior point methods is their ability to identify the essential subspace in which the optimal solution is hidden. What do I mean by this? It is this ability to identify what is basic and non-basic. And interior point method very quickly focuses all the computations on the basic part. Basic is not understood in the same way as in the simplex method. Basic is understood as the set of variables which are likely to be non-zero at optimality, and non-basic, the set of variables which are likely to be zero at optimality. In the next part of the talk, I'd like to go beyond the obvious things of interior point methods. So I'll show you that we can relax a lot of requirements normally used in interior point methods. We do not have to be very rigid. We can do things much more aggressively. Up to the point of this recent development, which is a very, very inexact method developed by my PhD student, Filippo Zanetti. But I also would like to draw your attention to other ways of defining homotopies, homotopies similar to interior point, which would require using some form of Newton method, but in this case, very inexact Newton conjugate gradient method. And at the end of my talk, I will concentrate on a variety of sparse approximations with interior point methods, sparse approximations which come from machine learning, from image processing, and different applications. Do you have any questions concerning the second part of the talk before I move on?
Jacek, if I may ask.
Yeah.
So, you know, this optimal partition is very particular to linear programming.
Yeah.
So, like in a semi-different programming, it's already a very complicated issue. So are there any similar ideas for preconditioning in semi-different programming?
But my only experience with SDP preconditioning was a very, very special SDP type, the matrix completion or the low rank SDPs. So if you think of low rank SDPs, a lot can be achieved. It can be the facial reduction, like the things that Henry Volkovich is doing. There may be specially designed preconditioners that exploit it. Many people did it, including myself, but many people did it before. So for general SDP, of course, there were works by Kojima and Kim Chuan-Toch, but this was mostly using the heavy tools like parallel computers to
Yeah, no, I'm more thinking in terms of your analysis, you know, where you are focusing on the basic variables. And I mean, I just simply do not see how this would work in semi-different programming, such an analysis.
If you would allow yourself to say that in SDP, the capital X times capital S should approach identity and approaches identity through me times identity, then naturally there is a rank of X and rank of S that is revealed at some point. The one of these matrices may have a noticeably smaller rank than the other. And if this is the case, then maybe some kind of approximation of this lower rank object, either X or S, would be the way forward. But how to do it in general? Oops, tough question. I don't know.
Very clear. Thank you.
Right. Let me go to the applications, and I'll start from relaxed interior point method. And by the way, this is done in the context of SDPs. So SDP is still a challenge, computational challenge. When I say SDP, I mean general SDPs, because for specific SDPs, people have done an amazingly good job and demonstrate that large problems can be solved. But there is always something special about these SDPs. I'd like now to look at the general SDP and relax the rigid structure of the method, replace exact Newton with an inexact Newton, try to do it in matrix-free, limited memory regime to avoid the curse of SDP, the curse which means, oh, it requires awful lots of memory. Clearly, the preconditioners will be essential to if this ever is to be successful. So here's an SDP in standard form, the primal and the dual. And suppose that we deal with a situation in which S is a sparse matrix. If S is a sparse matrix, then ideally we should never ever formulate the matrix X, because even for sparse S, X may be pretty dense. And many problems are given to us in this form, and we do not really realize the fact that they are not necessarily given in the best form, that trying to find what X is may require much more work than necessary. Frequently, S, being a combination of C and matrices AI, inherits sparsity from the fact that C and matrices AI are ridiculously sparse. If you think of matrix completion, AI has just 2 non-zero entries. So if you do not have too many of them, S would still be pretty sparse. C is often diagonal. Okay. So look at the dual barrier problem, in which we would like to maximize this dual barrier, well, dual plus the barrier function. So we removed the requirement that capital S is positive semi-definite. We just keep this requirement implicit. And in such case, X will be represented only implicitly as the inverse of S. Optimality conditions are written down here. Primal dual complementarity condition, of course, is always the same. And it means that even if S is sparse, X may be quite dense, because the inverse of a sparse matrix may be a very dense matrix, almost completely dense. We looked at this problem and we decided to use interior point in a very relaxed way. That is, we will update the barrier term very aggressively from me to maybe 0.1 times me in the next iteration, but then we will allow more Newton iterations, and to be precise, inexact Newton iterations, trying to find new optimality conditions, to be precise, get closer to satisfying the new optimality conditions for the updated value of the barrier parameter. So we implemented such an algorithm in which the stopping criterion was just, well, think for a moment about it. What it really means is that I'd like the Newton step in the variable S here, in this variable S, to be small relative to S, because it is pre-multiplied and post-multiplied with S to power minus half. So this, Frobenius norm, means that Newton step is small in relation to the current iteration S. We implemented such a method, and we could see that for certain problems on which the matrix S is really very sparse, it behaves better than the general SDP. So I think there is a room for looking at interior point methods and asking yourself how much of the optimality conditions, how strict should we be about imposing optimality conditions? Maybe some of them could be relaxed, could be just ignored, and the method would still behave well in practice. It was done like this. It works well, but after relaxing some of the conditions of interior point, we also had to say bye-bye to the beautiful complexity result of it. So there is a negative. There is a price to pay for computational efficiency. My second observation is about inexact interior point methods. I already tried to convince you that Newton method can be replaced with an inexact Newton method in which small error will be admitted. And as long as the small error is only a fraction of the right-hand side, the method would behave well. But I have to tell you that even such a method may occasionally be amazingly conservative and disappointingly slow. So why shouldn't we be even more daring, even more brave, and say, well, do we really have to satisfy this condition? Maybe we can relax this condition even further and still enjoy a fast convergence. And that's indeed what we have done with Filippo Zanetti, with my recent PhD student. I'll show you what happens in a particular interior point iteration when you apply conjugate gradient to solve the normal equations. Conjugate gradient method is non-monotonically reducing the residual, the error in the Newton direction. It starts from a large error, 10 power minus 1, and then after 10 iterations, we reach 10 power minus 3. After 20 iterations, 10 power minus 4. After about 60 iterations, we get to 10 power minus 6. But if you look at what happens to the quality of the direction, then you might actually realize that after about 17, 18 iterations, primal infeasibility and dual infeasibility and complementarity are already reduced as much as they will be reduced by even more precise direction. Primal step size has been correctly determined after 16, 17 iterations. Dual step size has been correctly determined after about 17, 18 iterations. Now, you look at these pictures and you would ask yourself, why on earth should we waste time from iteration 18 to iteration 60 to reach the exaggerated accuracy in the conjugate gradient, exaggerated to be equal to 10 power minus 6. We should stop the method somewhere here because the Newton direction already has all the necessary information that we need to perform one interior point iteration. So we designed a criteria which reflects to this situation, and this criteria is given here. It checks how the Newton direction component-wise behaves in relation to the iteration in the primal space and in the dual space. And we also ask for infeasibility in the primal to be reduced by certain amount, eta k, and infeasibility in the dual also to be reduced by certain amount, eta k. And we implemented these conditions. By the way, we analyzed what happens to the complexity of interior point method in such a situation. The complexity drops. It drops from O of n for large step method to O of n squared. Okay, that's a bad news. We will have the algorithm which theoretically may behave less well. However, in practice, using this stopping criteria for the Krylov method really delivers an amazing improvement, because we can cut down 70 to 90% of useless Krylov iterations, which would reduce the numerical error, but would not necessarily improve Newton direction. So why should we waste time on it? We have implemented it both for normal equations version, for conjugate gradient, and for augmented system. Then we needed to use mean rest as the numerical method. It's been done. It gave us quite nice results on a variety of problems. And the paper has been submitted for publication and sunk in the journal. It's now 7.5 months that we wait for the referee report. But yeah, I won't complain about it. One could think that when conjugate gradient method is used with a fixed tolerance, then at certain interior point iterations, many CG iterations would be needed. You see, at iteration 1, these are interior point iterations, these are conjugate gradient iterations. At iteration 1, we would have to do nearly 500 CG iterations. What a waste of time. We don't need it. If we use this intelligent stopping criterion, we will stop after 40 or 35 iterations. And the quality of Newton direction is equally good as if we went for the full 500 iterations. So doing this, we can have this bottom curve here, which limits the number of Krylov subspace iterations and delivers a much more efficient interior point method. We used it in a very difficult problem originating from X-ray tomography. This problem tries to find the solution of a least squares problem, which are regularized by two types of regularizers. This is a Tikhonov type regularizer, the convex quadratic regularizer, but this one is very ugly. This is a so-called inner product regularizer, which promotes material separation. So in X-ray tomography, you use X-ray tomography, for example, to analyze artifacts. In the Netherlands, you might use it to see what is hidden under the picture of Van Gogh. Maybe there was another picture that he painted, but then he was unhappy and repainted a new picture on top of another picture. Okay. And if you want to do this kind of separation, you will use clever X-ray tomography that is able to distinguish between different media through which the signal passes. And distinction, the separation, is extracted by the use of this non-convex regularizer S. So the problems are non-trivial. And what we could see is that if we use the standard implementation of interior point method with standard conjugate gradient, going for 6-digit accurate solution, then we would require many CG iterations and we would waste a lot of time. If we use an intelligent preconditioned conjugate gradient with this new stopping criteria, then significantly fewer CG iterations are performed. You see, instead of 25,000, we would do 2,600, so it's about 10 times fewer iterations. And of course, this also leads to significant reduction of the time. This is done in a paper published in Inverse Problems. I mentioned this problem originating from X-ray tomography, but we also use the same criterion in some PDE constraint optimization, and it also allows us to stop Krylov method much earlier than if we went for the standard stopping criteria. My next part of the talk will concentrate on big data optimization. And to be precise, on sparse approximations. And those can originate from machine learning or from computational statistics when we want to estimate X from observations, or signal processing and compressed sensing, a very, very sexy area that engineers are excited about. All such problems lead to some dense, possibly very large quadratic programming problems. To illustrate the advantages of using sparsity, promoting sparsity, I show you here a trivial example in the space of dimension 2, in which we look for a separating hyperplane. In the first case, we promote sparsity of the solution by penalizing for norm 1 of vector x. While in the second case, we use Euclidean norm as a regularizer. And what can one observe in this binary classification is that, well, for my very easy test example, it was possible to separate the two data clusters by using only one component of the vector. And indeed, this separation was spotted if we here promoted sparsity in the solution by using norm 1 of the vector. This would not happen if we use Euclidean norm, because Euclidean norm tries to average the error. Well, that's the nature of Euclidean norm. The Euclidean norm penalizes for all components. Norm 1 penalizes only for the sum of all components. So it promotes that fewer components will be non-zero. The vast majority of them will be equal to 0. In dimension 2, this example will not convince you, but think of this in dimension 2 billion. And in dimension 2 billion, if we can find a separation by using 1,000 or maybe 5,000 components instead of using all 2 billion components, it is very important. This is how sparse approximations become attractive in very large, in the analysis of very large sets, clustering very large sets. So we will look at L1 regularization, the problem like this, and you may think of least squares regularized with norm 1. Here is the usual least squares objective, but instead of only finding x, which minimizes this error, the square of this error, we would also like the vector x to have as few non-zero entries as possible. And this is achieved by adding this L1 regularizer. This is an easy optimization, you would tell me immediately. There are no constraints in this problem, so it cannot be complicated. But there is a little issue here. This is the non-differentiability of norm 1. Norm 1 is the sum of absolute values of entries of the vector, so it is non-differentiable. And how can we deal with it? We can either split every component of the vector, split the vector into positive and negative part of it and keep both non-negative, or we can use the smoothing. We can use an approximation of the cask, because the function is non-differentiable on such a small set that we could approximate it with some other function and easier to deal with. There is an example of pseudo-Huber function. This is the pseudo-Huber function. Instead of an absolute value of x, the blue line, we would have this function which is green here, which is almost the same everywhere further away from 0, but close to 0 would behave, well, you may say, like a quadratic function. Anyway, the function that is infinitely many times differentiable, so we will be able to use Newton method for it. Two ways of continuation can be proposed for these L1 regularized problems. and two types of homotopy approaches. One of them is, well, replace absolute values with the splitting u minus v, keep both u and v non-negative, and because they are non-negative and we know what to do with inequalities, there is nothing better to handle inequalities than to use interior point methods. So use interior point methods, replace these variables with logarithmic barriers, and drive the parameter mi to 0. An alternative is use pseudo-Huber approximation, that is, replace every absolute value of xi, vector xi, with this pseudo-Huber function, and then take the parameter mi to 0, just like in interior point, although the meaning of this mi is very different. The meaning of this mi is just a parameter which approximates the pseudo-Huber function here on the picture. If you choose small mi, the approximation will get closer to the blue line. For this methodology, we should ask questions: is it theoretically sound? Is it can it be made attractive in practice? And the answer is positive to both these questions. So for compressed sensing, we looked at problems which are more difficult, which originated from image processing, really. And instead of just dealing with least squares and promoting sparsity of x, we had to promote sparsity of x in a different dictionary. So that's like wavelets or some other space in which we would like not just x to be sparse, but w transpose x to be a sparse vector. To deal with it, we replace this norm 1 with a pseudo-Huber function, C mi, and then ask the following question. If we want to solve the true problem, it will give us the optimal solution x tau, depending on the weight on L1 term. If we solve the pseudo-Huber approximation, we will obtain a different solution depending on how strong the approximation was, how big mi was. But the question is, can we guarantee that if we take a sequence of these values of parameter mi, decreasing sequence, then the solution obtained here will eventually go to the solution x tau? And the answer is positive. Yes, we can prove it. We can show that, well, under many conditions. My theorem stated here is given in a very brief description. If we do it carefully, then we can prove that the distance from the solution x tau mi to x tau in 2 norm behaves as O of square root of this parameter mi, which means that if mi goes to 0, the error will also go to 0, which means that we can, by performing several steps like this, starting from larger mi and then decreasing it, gradually approximate the solution of the true problem. Again, this has been done both from theoretical point of view and also from the point of view of designing the suitable preconditioner. So you can check details in the paper. But I'd like here to convey the idea of the generality of it and the idea that, yes, we can use preconditioners for specific problems and use interior point methods to solve them. This development, by the way, made me acutely aware of how the community lacks proper testing mechanism for these L1 regularized problems. So together with Kimonas, we designed a MATLAB code which produces good test examples. It constructs a matrix A by assuming its singular value decomposition, where matrices U and V are orthogonal matrices constructed by Given's rotations, and we can control sigma, we can control the condition number of the problem. And that way we can produce problems which are easy or more difficult. And then we run lots of tests, because the literature nowadays is full of various first-order methods applied to solve specific L1 regularized problems. So we run a lot of tests for relatively small problems. The dimension did not exceed 1 million. And we run 4 algorithms: FISTA, parallel coordinate descent method, this projected scale subgradient method, and our primal dual Newton conjugate gradient. And what we could see on these tests, by the way, it took a lot of sweating by the computer. Overall, the computer was working for 4 months to run all these tests. And what we could see is that the first order methods work well as long as the condition of the matrix is small. It does not exceed 100. They start to struggle if the condition number exceeds 1000. They completely stall. They do not converge. They can spend eternity cycling like a Brownian motion if the condition number grows. It's not a surprise that the second order method, the method which uses a little bit of Hessian information, even simple with a simple diagonal preconditioner, can push the class of solvable problems further and can deliver solutions for problems with condition number going up to 10 power 6. You may ask me, what should we do if the condition number goes further than that? Well, the answer is obvious. We should invest more in the preconditioner. We should do something cleverer than just diagonal preconditioner. Diagonal is really very simplistic. This is the very cheap, but at the same time, overwhelmingly simplistic preconditioner. So if you have something worse, something more challenging, you need to design a better preconditioner for it. And then we run very large problems. Edinburgh is a place where there are parallel computers, very powerful parallel computers. So we could go with this problem up to size 1 trillion. Here you see the problems of size expressed in billions. So 1 means that this was the problem with n equal 10 power 9. This is 4 times 10 power 9 up to 1000 times 10 power 9, which is 10 power 12. But to be able to solve these problems, we had to use many processors. And of course, when we solve the problem 4 times larger, we also use 4 times more processors. And we use 4 times more memory that you can see here. But we do not increase the time, which means the primal dual Newton conjugate gradient method on this specific problems is a perfectly scalable algorithm. Whether you solve a larger problem or smaller problem, under the condition of having enough processors, you can solve all of them in about 2000 seconds. But this was a kind of academic example, just pushing the size of the problem to ridiculous dimensions of 2 power 40. In my last few slides, I would like to tell you about different sparse approximations that have been developed over the last, say, 3-5 years. And for all these problems, there have been very specialized first-order methods designed. And when I talked about it with Daniela Di Serafino, one of my collaborators, I just asked her, why don't you try to use interior point method to solve all these problems? And we decided that we will specialize interior point method for all these problems and see how interior point compares with these highly specialized first-order methods. Applications are very different. They change from portfolio selection to classification models using functional magnetic resonance imaging, total variation-based Poisson image restoration, or linear classification via regularized logistic regression. In each case, we compare interior point, generic interior point, with the best possible first-order method for this specific problem. So for portfolio, this is split-Bregman method. For magnetic resonance, we compare it with FISTA and ADMM. For TV-based Poisson image restoration. This is the Primal dual augmented Lagrangian, PDAL. And here for linear classification, the problems used in this for this application are the very good codes are the new GLM net and ADMN again. And all our results are summarized in this paper, which will appear in Science Review. But I will now concentrate on just one of them because it illustrates well what happens when you use interior point method as opposed to first order methods. So this is the classification models with functional magnetic resonance imaging. And interior point method here will be compared against FISTA and alternating direction method of multipliers. We will report 3 criteria. This is the classification accuracy. This is the corrected pairwise overlap, which measures the stability of every voxel selection, and the density. The density is the opposite to sparsity. When I say we want sparse solution, we would like density to be as small as possible. Accuracy, we would like it ideally to be 100%. Corrected overlap, we would like it to be as high as possible, ideally close to 100%. Density, we would like it to be as small as possible. So remember, these two numbers should be large, this one should be small. What happens when you use interior point method? What happens when you use FISTA or ADMM? Look at that. ADMM is completely unable to deal with corrected pairwise overlap. Here, these numbers should be close to 100%. They are nowhere near. FISTA manages to handle it, eventually gets for tau equal 10 minus 1, it gets to 80%, which is not bad, but interior point method gets much better result, 82.6%. This is the quality of this corrected pairwise overlap. If you look at density, ADMM is completely unable to detect sparse solution. This is the sparsity 97, 98%, which means the solution is completely dense. Almost all variables are non-zero. Interior point method spots very well density, sparsity, I mean, produces solutions which have only 2.5 or 4% of non-zero entries. For tau equal 10 power minus 2, which means lower penalty for sparsity, of course, more entries are present in the vector. Now, it's very interesting to see how these features are revealed when the algorithms progress. Here is the behavior of interior point method, and here is the behavior of FISTA. So if you use, maybe I'll start from FISTA. If you use FISTA, very quickly you will obtain a reasonably accurate solution with density of about, what, 15%, and correlated overlap about 70%. And then it will take a long, long time to get it improved, but it is improving. It will take awful long time to get density, sparsity down to the same what was achieved by interior point. Interior point had no clue what is going on for about 10 iterations. After about 10 iterations, optimal partition settled, then quickly was polished. And after 16, 17, or maybe 18 iterations, everything is optimal here. You won't be able to get any better solution with any other method. You could stop interior point after 20 iterations, giving you very good sparsity of the solution, about 3%, and also very good accuracy and corrected overlap, both equal about 80%. FISTA gets to this 80% after about 20-25 minutes, but sparsity is still very poor. So this summarizes
Jacek,
my experience. Yep.
for interior points, it's time or iterations on the x-axis?
Here we have time. Everything is measured in time to just avoid the situation that a single interior point iteration is very different computationally from a single Vista iteration.
Yeah, okay. Yeah, because you said after 10 IPM iterations, but...
Apologies, after about 10-15 minutes. Sorry.
Okay, yeah, thank you.
Yeah.
Thank you.
Time in minutes here. So, without repeating myself, there is a different way of approaching optimality. Interior point method quickly spots, after a while, after several iterations, spots which variables should be zero, which should be non-zero, and then polishes the solution and gets to the optimal solution. First order methods approach it in a different way. And sometimes can take a long time. You would have here to go for hours and hours to get to the same level as interior point method got. But I've been pushing your patience for quite a while, so let me get to the conclusions of my talk. I'm certainly fascinated by how interior point methods have changed the area of optimization. They really produced something like a little revolution in interior point. And they are, of course, second order methods. They do rely on Newton method, but the point is we do not have to use exact Newton method. We can allow ourselves a lot of flexibility in playing with inexact method and still deliver high quality solutions. The tricks which make it work are continuation understood in interior point by changing the weight on logarithmic barrier, but we can go out of interior point framework to primal dual Newton conjugate or to Huber approximation and use also similar type of continuation. And we still enjoy this property that an essential subspace is revealed relatively early, and once it is revealed, interior point methods can be accelerated. Their implementation starts to deliver the solution quickly. This can be achieved by exploiting linear algebra, but the beautiful thing about interior point is that you can solve various classes of problems with virtually the same algorithm, but you can also go outside of these classes of problems and use Newton CG for L1 regularizations, or use dedicated interior point methods for sparse approximations. And this was my last slide. Well, actually, the last slide is thanks for your patience, for your attention. I hope I managed to convey a little bit of my enthusiasm for interior point method to you, and otherwise stay safe, stay healthy. It's a shame we couldn't see each other directly, but yeah, these are the times we are living in. Thank you.
Okay, thank you so much for the very nice, interesting talk. Let's see if there is any question from the participants. Okay.
Can I just return to my question at slide 56?
Michał, you were saying something?
Yeah, can I just return back to slide 56 to the question I already had?
Which slide was it?
56.
There you
go. Okay, you say it's time for interior point method, but I would say it's quite similar to iterations, isn't it? Iterations there.
Say again, Michał. I needed to put the voice up because I can, yeah.
I presume the time for the interior point method more or less corresponds to iterations, doesn't it? You don't need too many interior point iterations there.
That's true. Interior point usually converges in, say, 20, sometimes 30 iterations. If the problem is really, really tough numerically, may need more, but the number of iterations is very predictable for interior point.
Yeah. Yeah, thank you.
Yeah. But one iteration is costly, significantly more costly, for example, than Vista. So thanks for spotting it, Michał, because indeed I said something which was not true. Let me indicate it once again. These are the time. This is the time in minutes, not the iterations. But it would not surprise me if 10 minutes here would mean 10,000 Vista iterations, or maybe 50,000 Vista iterations, while 10 minutes here would mean probably 10 interior point iterations.
Jacek, if I may ask a last question, it's quite general. So you showed that you can compute the inexact Newton direction using conjugate gradient with preconditioner in many settings, but quite often the bottleneck is to form the Newton system, to form the linear system. So can you say something about that?
That's an incredible advantage of iterative method, because if you have a way of formulating your constraints as operators, then maybe you will completely get away from ever formulating them as matrices. It's I would really need to go very, very far back, maybe somewhere here. No. Just give me a second. I'll find the. Oh, okay. If you know that there is a special structure in matrix A, then you might be able to solve this system of equations by an iterative method without ever formulating matrix A theta A transpose. Because what iterative method needs is only the multiplications with A transpose, then multiplication with theta, which is diagonal matrix, so this is trivial, and then multiplication with A. I did it in a number of applications in signal processing, for example, in image processing, that these equations are never formulated. They are handled entirely implicitly, entirely matrix free.
And just a comment, you can do it for semi-refinite programming as well, for nesting of thought, for instance, direction.
Say again, Michał.
You can do it, for instance, for nesting of thought direction in semi-refinite programming as well. Yeah. You don't need to formulate it. You use the operator form.
Yeah. The issue always is how to precondition and how to construct a precondition of this matrix without formulating the matrix. And that's a little bit a tricky thing, because the typical linear algebra approach of people is, oh, build this matrix, sparsify it, and then get the preconditioner. So this is, I would say, the heavy way of doing it, which works fine in many applications, but we would like to have something cleverer than that. We would like to formulate the preconditioner for the matrix without formulating the matrix. On many applications, we know how to do it. Please say it again, because I had difficulties in understanding the question.
I think it wasn't a question, it was just unmuted by accident.
I see.
So, are there any further questions?